So, in the previous two lectures we talked about linear momentum, and linear momentum is a very important physical quantity, and the law of conservation of linear momentum is one of the pillars, very strong pillars of our formulation of physics. But then the way we generally define it, P equal to m times v, mass times velocity, this quantity mass times velocity does not remain conserved even if there are no interaction, no forces, external forces on the system, and therefore, we need to redefine this linear momentum, so that we can still use that conservation ideas and the things which are derived from them. And as we had seen that if we define a quantity, if you have a particle of mass m, and then it goes with a velocity, let us say v. So, velocity is v, and then we define a quantity p which is mass times velocity, and then divided by square root of 1 minus square of this speed square v square by c square. If we define a quantity like this, then this quantity is conserved in collisions and situations where no external forces act, and this can act as a linear momentum. Now, this redefinition of linear momentum dependence on velocity in this particular fashion it works very well in all conditions, and therefore, we stick to it. But then people are somehow tuned towards that old definition P equal to mv, and they want to preserve that. So, there are two ways of doing that, right. So, one is that there are three ways. One is that you accept that momentum is not defined mass into velocity. Momentum is defined as mass times velocity and then divided by this factor. So, this is one way. But then if you want to stick to P is equal to mv, one way is that the mass of the particle, give another symbol to it, and then construct a mathematical quantity which is this. So, let us change our symbol, mass of the particle, let us write it as m naught, and then this quantity, this whole quantity, this much, we name it m, and then we say that it is mv. So, P equal to mv, right. So, this is our old very familiar beloved equation. So, we can still say that linear momentum is mass times velocity, but the mass is, this mass is different from the mass of the particle as we know, as it is written in the textbooks. Mass of the electron is 9.1 into 10 power minus 31 kg, proton mass this much, neutron mass this much, mass of a helium nucleus this much. So, that mass is a property of the particle, just like a particle has a particular charge. Similarly, a particle has a particular mass, electron has a particular charge, electron has a particular mass. E by m ratio has played a very crucial role in development of all this modern physics, you know that. So, mass is something which is a property of the particle, and then if the particle moves with a speed v, then you construct this mathematical quantity which depends on what speed particle is moving, and you will have to give a different name. This is not mass. So, you will have to give a different name, and that name given is, so this is m, this m is m naught divided by square root 1 minus v square by c square, and this is called relativistic mass. So, I am very clear about it, and I want to convey this, that this relativistic mass is a mathematical construct It is a quantity that we have constructed. Mass of the particle is here, and this is a quantity that we have constructed, and we have given it a different name. It is relativistic mass. So, if I say just mass, I will be referring to mass of the particle. Okay. To give any kind of to avoid any kind of confusion, this is also given a different name, and that is called rest mass. Right. In this, if I put V equal to 0, m is equal to m naught. So, if the particle is at rest, then its relativistic mass is the actual true mass of the particle. Right. So, if the particle is at rest, that time its relativistic mass and its mass, they are same. So, in that fashion, treat this as rest mass and this as relativistic mass. In this equation, if I replace this rest mass or the mass of the particle by this relativistic mass, this equation works well, but it is very limited use, not always. For example, we have force is equal to mass times acceleration. Now, if you think that okay, I will use relativistic mass and that F equal to mv will just work, just like this P equal to mv is working with relativistic mass, it does not. It does not. So, okay, this is a good quantity, this is a fine quantity, and it does have some significance also, but nevertheless do not give it status of mass of the particle. So, that is my request. So, this is one way. Another way, there is another way, we can still work with only one mass, which is the intrinsic property of that particle, and then we can still preserve this if we say that in this equation what we will do is P is equal to mass of the particle times velocity divided by square root of 1 minus v square by c square, and this quantity we rename. Another mathematical construct. This is one mathematical construct and this is another mathematical construct. This was mass and this was given a name relativistic mass. This is velocity, and then velocity divided by square root 1 minus v square by c square, we give another name, we call it proper velocity. So, we call it proper velocity, proper velocity. I will just tell why it is called proper, and given a symbol generally this eta. So, eta is actual velocity divided by square root 1 minus v square by c square. So, you can absorb this factor with the mass, or you can absorb this factor with the velocity. If you absorb this factor with the velocity and say that we will be using proper velocity, then also you have the same relation, P is equal to mass times velocity. So, this is another way to preserve our definition. Linear momentum is mass times velocity, but this velocity is not the ordinary velocity. This velocity is something different and it is called proper velocity. Now, let us see what this velocity is, and is there any meaning, physical meaning of this proper velocity. So, how do we define velocity? How do we define velocity? Let me take symbol u for the velocity of the particle, because we will be talking of changing from one frame to other frame, Lorentz transformation, and the frame velocity we had been using that small v. All our Lorentz transformations are written in terms of that small v. So, for the particle velocity, let me use the symbol u. Okay. So, how do we define ux, x component of the velocity of the particle? This is dx dt, and that means what I do is I take two events. Particle is here at x, y, z at this location and at this time t, and then as time elapses, a very short time interval, t plus dt, the particle reaches somewhere else. So, this is t plus dt time, and the particle is at x plus dx, y plus dy, and then z plus dz. Proper calculus language should be used. We can write this some delta x and then delta x tending to 0, etc. But essentially this is what the physics is. At time t, the particle is at x, y, z. At time t plus dt, the particle is at x plus dx, y plus dy, z plus dz. And then we say that this dx, change in the x coordinate, divided by this dt is this ux. Of course, you have to take limits and all that. So, you have two different events, one event, another event, and then take this dt and take this dx, and that gives you ux. Similarly, uy and uz. Similarly, uy is this dy by dt, and then uz is this dz by dt. What is eta x? Look at here. What is eta x? Eta x is ux divided by square root 1 minus u square by c square, right? Particle speed here and velocity here, x component. So, x component. So, it is this. So, this is equal to dx dt. Ux is dx dt, and then square root 1 minus u square by c square. Now, look at these two events. These two events are occurring at two different positions in this frame. In whatever frame we are using, the frame in which the particle is moving with velocity u, in that frame we are talking, and this event occurred here and that event occurred somewhere else. So, these are two events occurring at different positions, and the time interval between these two events is dt, which is not the proper time interval. What is the proper time interval between these two events? You remember? What is the if you change frame, this time interval will change. So, if you can find a frame in which the two events occur at the same place, the time interval between these two events in that frame is called proper time interval, and which is the shortest of all such time intervals. So, if I say that this is in frame S, this whole picture is from S frame, and we go to some other frame which is moving in x direction with velocity ux, okay, moving with respect to s with a velocity say ux or u in fact, the particle is moving with velocity u and my frame is also moving with velocity u. So, actually I have gone to the particle frame, okay. Locally at that instant I have gone to the particle frame, and in that frame the particle is at rest. The two events still occur, but then the other all clocks etc. are moving, and at the same position of the particle I am measuring the time interval between these two events. And proper time, that will be the proper time interval, and the proper time interval d tau will be shortest, remember. So, dt in this time in this frame it is dt, and times what is the velocity of the frame in which the events are occurring at the same position, that velocity is here, and so 1 minus u square by c square. So, this is the proper time interval between these two events, and this quantity is here. So, this is dx by d tau. So, this so called proper velocity x component is dx divided by length divided this distance covered divided by time, that is the definition of velocity. So, distance covered is here and time is here, but which time? The time in the particle's frame. Okay, in the particle frame some time has elapsed and then some other clock is coming here. So, that is the proper time interval, and that is why this velocity is called proper velocity. But remember, this is a mathematical construct, because what we are doing is dx we are measuring in frame S, this is measured in frame S, and d tau we are not measuring in frame S, this we are measuring in the frame of the particle. Okay. So, time interval we are measuring in a different frame, the separation in space we are measuring in some other frame, and then we are dividing this length by this time to get some kind of velocity. So, this is also a mathematical construct. So, this is known as a proper velocity, and in this terms p is equal to m naught into eta, that linear momentum is mass times velocity. That definition can still be used if I use this kind of velocity. So, one is mass, you redefine or you define a new kind of mass, call it relativistic mass, and the other approach is that you define a different kind of velocity and then you use that same definition. So, that is about these things. Now, this proper velocity that we have defined has a very good use in theory of relativity, because you can construct a velocity 4 vector or 4 velocity. Remember, any vector that transforms according to that Ct x y z, right. If in a frame there is some event at x y z at time t, and if you write Ct x y z, that transforms according to the Lorentz transformation, and we call it 4 position or position 4 vector. Okay. So, if this is position 4 vector and then at t plus dt, so this t plus dt and x becomes x plus dx, y becomes y plus dy, and z becomes z plus dz. This is also a 4 vector, it is a position of the particle, right, it is position of the particle at a given time t. So, when we construct these 4 components, this is your temporal component and this is your spatial component, and we combine all these 4 together, this becomes a position 4 vector at time t. Then position is changing, time is changing, correspondingly position is changing, and therefore, at time t plus dt you have this as the position 4 vector. So, this is a 4 vector, this is a 4 vector, and this transforms according to Lorentz transformation. If I change the frame, then I know that time is different, x is different, y is different, z is different, and then the Lorentz transformation will relate the two. Similarly, here this also at this time also you have position, you have time, and you can do a Lorentz transformation. And therefore, if you subtract, what you get is c times dt and then dx and then dy and then dz. Okay. So, this is also a 4 vector, 2 vectors, you add them, you subtract them, do not multiply, okay, or do a linear combination, that also is a 4 vector. So, this is also a 4 vector. Now, I multiply everything by a constant, then also it will remain a 4 vector, just a constant. So, if you do the Lorentz transformation, that constant is, you are just carrying that, other things are all same. So, if you multiply this 4 vector by a constant quantity, all the 4 components, you still get a 4 vector. So, let me multiply it by 1 by d tau. There is a proper time interval between these 2 events. At time t, the particle is x y z, one event. At time t plus dt, the particle is at this position, another event. What is the proper time interval between these two events, that is d tau. Okay? In whatever frame you are working from initially, proper time interval is the proper time interval, it is the time interval measured in the particles frame, right. So, if I multiply everything by 1 by d tau, what I get is c dt over d tau, this is 1, then dx over d tau, this is another, dy upon d tau, this is another, and dz upon d tau, that is another. This is a 4 vector, and this quantity is c times dt by d tau. What is dt by d tau? This is d tau. Dt by d tau is dt by d tau is dt by dt 1 minus u square by c square. So, it is 1 by square root 1 minus u square by c square, which you can write gamma u. Let me write it u to remind that it is not the frame velocity with which we are talking all these things. This is the particle velocity in the frame in which I am working. In one particular frame I am working. In that particular frame the particle is moving with velocity v or u, and with that corresponding u I have this quantity 1 by square root 1 minus u square by c square. If I change frame, if I change from s to s prime, some s prime, the velocity of the particle will change. If the velocity of the particle changes, the speed of the particle changes, then this gamma will also change. So, this will have different values in different frames. So, let me just put this u here to remind that the speed of the particle is u here. So, this is c into gamma times u, and this quantity is eta x, this quantity is eta y, and this quantity is eta z. This is a 4 vector. So, if I write it in a proper column form, this will be like this. It is c times gamma u, and then eta x and eta y and eta z. This is a 4 vector. This is a 4 vector, it will transform like this c t x y z, same Lorentz transformation will be used, and this is known as this vector is known as 4 velocity or velocity 4 vector. Okay. If all this is written from say frame S, if I go to frame S prime, what will happen? You will have different values of all these things. So, let me put it prime here, prime here, prime here, and prime here, prime here. Here also prime. I am writing all these things from S prime frame. In S prime frame, the particle velocity is not u, it is some u prime, and therefore, you have u prime here. When you are constructing this quantity, you will put u prime here. S prime frame, from S prime frame I am writing all these things, and this will be equal to the Lorentz transformation matrix. Remember, gamma minus beta gamma 0 0 and minus beta gamma gamma 0 0 0 0 1 0 0 0 0 1. This is your Lorentz transformation matrix, and then here you write the quantities in S frame. So, it is c times gamma u, and then you have eta x, eta y, and eta z. So, this will be the transformation of this 4 velocity 4 vector when you go from S to S prime. In S you have these quantities, and in S prime you have these quantities, these components. So, you can immediately write what is eta y prime. Okay. You remember, for this transformation you have, if you write this as c t prime x prime y prime z prime, and then that Lorentz transformation matrix, and here c t and x y z, you very well know that this quantity, this third component 0, 1, 2, this 0th component, first component, second component, this y prime is equal to y and this z prime is equal to z. Same story, 0th component, first component, second component, third component. So, eta y prime will be equal to eta y. The y component of proper velocity remains unchanged if frame s prime is moving with respect to s in x direction. Similarly, here eta z prime will be eta z. And of course, you can always write the transformation for this and transformation for this. You know how to write transformation equations for this. Exactly the same transformations will be here. So, that is the meaning of being a 4 velocity. It transforms just like the disposition 4 vector using the same Lorentz transformation equations. So, that is why it is this. I will pick up one more 4 vector before I close this. Let me make some space. So, this velocity 4 vector is here. Now, you multiply all the components of this velocity 4 vector by the mass of the particle. And remember, when I say mass of the particle, it is mass of the particle. It is the intrinsic property of the particle, which people call rest mass also. I will also call it rest mass, but to re-emphasize, when I am saying mass, it is the mass. So, multiply this 4 vector, you have this 4 velocity, sometimes it is called 4 velocity and sometimes it is called velocity 4 vector. And that is your components are c times gamma u, and let me write in column form only, eta x, eta y and eta z. This is it. This is a 4 vector, velocity 4 vector. This is velocity 4 vector. Multiply it by the mass of the particle, so that you put a m naught here, m naught here, m naught here and m naught here. Right? All components multiplied by the same constant quantity. And therefore, this is also a 4 vector, it has to be 4 vector. It will also transform according to the Lorentz transformation when you go from S to S prime. Now, remember what is this? What is this? M naught times proper velocity. This is linear momentum x component. This is linear momentum y component. This is linear momentum z component. So, you have m naught c gamma u and then px, py, pz. So, your linear momentum x, y, z components of linear momentum are part of a 4 vector, okay, spatial part of the 4 vector. This 0th component is called temporal part and these 3 components are called spatial part. So, the linear momentum, if I define it in this way, this m naught times v divided by square root 1 minus v square by c square if the particle velocity is v. If I define it that way, this is also a 4 part of 4 vector and this is called 4 momentum or momentum 4 vector. Okay. So, whatever is the speed of the particle, correspondingly you construct this gamma u, and then the first component is mass of the particle, rest mass of the particle times c times that gamma u, then you have px, py, pz. If you want to write this in terms of ordinary velocity, that also you can do. You remember how to write it. That will be m naught c times gamma u here. And what is eta x? Eta x is gamma u times Vx. Okay. So, Vx or Ux times this gamma u. This is m naught and then Uy times gamma u. This is m naught Uz times gamma u. So, this is how we had defined our eta x, eta y, eta z. Remember eta and velocity, they are related by if it is u, then u divided by square root 1 minus u square by c square, and s is gamma u, this u here, and then the velocity u. So, that is how we have defined proper velocity. So, if this proper velocity you can write in terms of ordinary velocity, then it comes like this. So, this is our 4 momentum vector. Okay. These 3 quantities you know, px, py, bz, these are the momentum components. What is this? What is this quantity? That we will talk in the next lecture.